Okay, next question on the list is 81. Draw the form that will predominate at pH 3, pH 6, 10, and 14. So basically, what the question is asking you is, you have an acid for these three different examples, A, B, and C, and your job is to figure out, as you increase or decrease the overall acidity of the solution, will your acid in question be protonated or will it be deprotonated? Will there be plenty of hydronium ions to give a proton to these compounds, or will the compounds really want to get rid of a hydrogen ion to give to the solution? Basically is what's being asked. Okay, so we have three different examples. We have a carboxylic acid, we have a ammonium compound, and we have an alcohol. So there are pKa's associated with each one of these, and by now hopefully you would have begun to memorize the approximate pKa. Obviously this number is going to change, it's not always going to be the same, but as long as you have a general idea of approximately what the pKa is, that's all I'm really interested in. So these numbers are obscured, but what I really want you to do is make sure see if you can figure out approximately what these numbers are before I reveal them. So go ahead and pause it, see if you can find the numbers on your own. Okay, so these are the actual pKa values for the carboxylic acid. Still about 4, 5, 4.8. This is going to be plus or minus a little bit depending on the structure. This guy, this ammonium, this guy has a pKa of 11. So this is actually a good time to take a second and really talk about this ammonium. So if you were to redraw this ammonium molecule, this nitrogen is going to have a total of 4 bonds to it. So let's take a second and see if I might have made a mistake here drawing this guy out. So every time you draw out a molecule, get in the habit of recalculating formal charge for your molecule if something was a little fishy. So specifically, the charge on this nitrogen is going to be, if you know, the valence for the nitrogen is going to be 5. So let's take 5. And we know we're going to have 1, 2, 3, 4 covalent bonds. So 5 minus 4, and we don't have any lone pairs in this case. Okay, so minus 0. And you might ask yourself, why don't we have any lone pairs? Well, if you attempted to put another lone pair on this nitrogen, you'd be violating the octet rule, which is a very simple rule, but people always mess it up. It's a very easy rule to violate, but the good thing is that it's also a really easy rule to fix. So at this point, nitrogen has more than its octet, so it's totally an invalid structure, so it's actually impossible for this nitrogen to have a lone pair. So I'm going to get rid of it. So at this point, the formal charge for this nitrogen really should be plus 1. So really this nitrogen should have a positive charge associated with it. So just to make a point, there are two forms of nitrogen, and going between the two actually has a huge difference on the pKa of that particular nitrogen and the hydrogens associated with that nitrogen. So let's compare and contrast. If you had this ammonium versus 1, 2, 3 versus this nitrogen right here. So this nitrogen has 2 hydrogens associated with it, and if in this case, right now we actually have less than the optimal number of electrons surrounding the nitrogen. You really only have 2, 4, 6. So if you wanted to complete the octet, which is always a good idea, you would include both of these electrons for the nitrogen. So now this nitrogen has its octet filled, and if we were to redo this charge calculation, we'd see now that the nitrogen has a charge of 5 minus 3 minus 2. It's going to be neutral. So this nitrogen right here has a neutral charge. This nitrogen up top has a positive charge. And this actually has a huge difference, or it has a huge effect on the overall pKa of the hydrogens associated with that nitrogen. So if we were to compare and contrast the two, we have now a totally different pKa for this nitrogen on the bottom. So this guy's going to have a pKa of about 35 or 40. And so notice this is a huge difference when you compare and contrast the hydrogens that are associated on the ammonium up top and the hydrogens that are attached to this amine down below. Okay, and it all has to do with the charge. Once you change the charge, you change the pKa. So don't fall into this trap of assuming that a charged and an uncharged amine have the same pKa, because they don't. Okay, so we'll go into this more a little bit later, but for now, just make sure you don't fall into this pitfall. Okay, next up we have our alcohol, and the alcohol normally would have a pKa of around 15. You might ask yourself why this alcohol is a little bit smaller pKa, why it's slightly more acidic. And going back to the previous question, we could really actually explain this away quite nicely, talking about electronegativity and proximity effects. So this is a good recap of the previous problem. Okay, so it's gonna the actual presence of these three fluorine atoms are actually going to depress the pKa and increase the acidity of this compound. Okay, so now going back to the actual question, I seem to be going off on tangents quite a bit. But question A, so the carboxylic acid, pKa of 4.8. So we want to see, at pH 3, 6, 10, and 14, what will be the predominant form? Will it be protonated or will it be deprotonated? Basically, that's what we're going for. Okay, so there is a very simple rule to help you get through this, and I'm just going to write it down real quick. So we have two if-then statements. If the pH is less than the pKa of the molecule, or if the pH is greater than the pKa of the molecule, we're going to have two different results. Okay. So in the first case, if the pH is actually going to be less than the pKa of your molecule, so say compound A, what will happen? We'll actually retain the protonated form of that molecule. Okay. And then the corollary to that is if you have a pH that's greater than the pKa of your molecule, then the deprotonated form will predominate. Okay, so in this case we have for the pH of 3, the pH of 3 is going to be less than the pKa. So in the first scenario, the protonated form is going to exist. Okay, at pH 3, this carboxylic acid is going to be deprotonated according to, or it's going to be protonated according to our rules. So it's going to look like this at pH 3. Okay. How about this positively charged ammonium? So the pKa is 10 at pH 3. The pH is less than the pKa, so we're going to retain that overall NH3 positive structure. For this neutral amine, pKa is 40, so in this case we're going to have pKa which is much higher than the pH, where the pH is much lower than the pKa. So this guy is going to remain just as it is. And I'm going to get rid of our rules. Get rid of them just for a moment. And talk about this alcohol. So at a pH of 3, pH is less than pKa. So we're going to retain this overall protonated form of our molecule. Okay, so really at this point nothing's really changed. It's quite acidic environment. Nothing's really going to become deprotonated. Okay, so next up in line, let's talk about pH of 6. So at pH of 6, for our first example, example A, the pH is going to be greater than the pKa. So you can imagine kind of at this point your solution that houses your carboxylic acid is getting less basic. There are less free H plus ions in solution, and so now it's going to be a little bit simpler for this carboxylic acid to lose its hydrogen. So now what's going to happen is the hydrogen on the carboxylic acid is going to be removed, and you're going to end up having this form of your carboxylic acid. And we're going to come back to this in a second, but for now I'm going to leave it. So for the protonated ammonium, the pH is still less than the pKa, so this guy's still going to be protonated, just like this. And for the regular amine, the pH is still way below the pKa for this ammonium, so it's going to remain the same. Nothing's going to change. And for this alcohol, the pH is still pretty much below the pKa of 12, so it's not going to change either. Okay, so CF3, CH2, OH. So other than for the first example, nothing's really happening. Okay, so but let's go back to this first example for a second. So what a common pitfall here is that at this point students have a bit of trouble trying to figure out whether or not this oxygen should be, neutral, should it be negative, should it be positive. So going back to the first example, let's think about how many electrons were around this oxygen. So we had 1, 2, 3, 4. Overall, we're going to have 2 lone pairs, and this oxygen is going to be neutral to begin with. Okay, so this is going to be a situation where it becomes really, really helpful to think about what happens in terms of electron flow and thinking about mechanisms. So thinking about what happens whenever you really want to get an H plus in solution. So we're going to have this form of the carboxylic acid on the left, and whenever we actually do this kind of acid-base equilibria, we're going to have an equilibrium arrow, and at the end of the day we're going to have H plus, and the way to figure this out kind of in an intuitive way is that you have to balance the charge on both sides of the equation. So if you're getting rid of H plus in solution, you definitely have to have a negative somewhere to make the overall right hand of the solution or equation neutral. So in that case, it's kind of intuitive that you need to make this carboxylic acid negatively charged. Okay, so we're going to put 1, 2, 3 pairs, and if you do a formal charge calculation, this oxygen is going to end up being negative. Okay. And the way you're going to draw this is, if you want to actually show this oxygen-hydrogen bond being broken, you're going to take the electrons that used to be in this bond, and you're going to push them over towards oxygen. So we're going to have 2 lone pairs to begin with, and at the end of the day we're going to have 3 lone pairs. One of the lone pair is actually coming from this old oxygen to hydrogen bond. Okay, so to answer that question, this guy is going to be negative. So for these other 2 pHs, if pH 6 is basic enough to remove the hydrogen, then pH 10 as well as 14 is going to be just as basic, or it's going to be more basic, but it's going to be just as good at removing a proton. So these other 2 forms are actually quite simple to write out. Okay, so they're both going to look like this. And then going to question B, so this ammonium, you have the ammonium, it's at pH 3, it's not quite basic enough to remove a proton, pH 6, not quite basic enough to remove a proton, and pH 10, it's getting close, but it's not quite there. So at pH 10, you'll definitely have some of the ammonium that's being deprotonated, but again, going back to the question's asking you which form will predominate, which will be the more abundant species in solution. So in this case, the more abundant species is still going to be the NH3+. Okay, and so same thing for the amine, still super high pKa, so pH 10 is not going to do anything to it. And if you go to the alcohol, same thing, pH 10 is still not quite above that pKa, so this form isn't going to change at all. Okay, and then finally, going over to the pH of 14, we're getting really, really basic now. So thinking about pH of 14 versus pKa of 10, the pH has finally surpassed the pKa of the ammonium, and so now we actually have a solution that's basic enough to yield a deprotonated form of this guy. Okay, so now at pH 14, since the pH is higher than the pKa, this hydrogen is going to be removed from the nitrogen, and it's going to be pushed into solution. Okay, and so this is kind of the second example. This amine is kind of working the same way as this top example for B, but again, since the pKa is 40, pH is not even getting near that pKa, so pH is still way below, and so still the predominant form will be that neutral amine. Okay, so if you actually could pull up a pH high enough, you could theoretically deprotonate it, but it's going to be really, really difficult. Okay, and then finally for the alcohol, the pH of 14, we've finally gotten a pH that's above the pKa. So since the pH is higher than the pKa, we're going to deprotonate this guy. And for the same rationale as above, how we're going to figure out what the charge on the oxygen to be, it's going to end up being a negatively charged oxygen. So make sure you don't forget that tiny little detail. It's a little minor detail, but it's super important to make sure that you get your point across. Okay. And I'll just go ahead and add all of the lone pairs right there. Okay, so overall, again, not a really difficult question. Just you have to have a good understanding of the relationship between pH, pKa, and at what point will a molecule be deprotonated, and at what point a molecule will remain protonated. So these are, again, going to be our rules. If the pH is less than the pKa, the protonated form of your molecule is going to predominate. If the pH is greater than the pKa, then finally you'll have conditions where you can deprotonate that compound to a very high degree.